Today we're moving on to Chapter 4, Day 2. We're going to be dealing with quadratics and quadratic functions. Looking back in the past, we've learned about how quadratics have a parabola-shaped graph. Remember that the vertex is the turning point where the max or the minimum occur, the minimum being at the bottom of the valley, maximums are at the top of the hills. Now remember that the parabolas have a symmetrical shape and that the axis of symmetry is a vertical line going right through that vertex. One thing to note that we're going to be using a lot of today is the vertex form of a quadratic function or quadratic equation. The vertex form is really helpful because the a value, if you look below, determines whether the graph opens up or down. If it is positive, then it opens upward. If it's negative, it opens downward. And then the most helpful part of the vertex form, just like it says in the name, is it gives us the vertex. So HK is the vertex. Remember, opposite inside, exact outside. That tells you the vertex. Now, when we're looking at our data, just like we did yesterday, if you recall yesterday, we used a data table to determine the line of best fit. So we used a bunch of data to create this line of best fit that could give us a better estimate of any future experiments or any future projections. So today we're going to be using that same table on this first page, but we're going to be doing a quadratic regression. We'll talk about that in a minute. A couple important skills here is make sure that we're confident in our ability to complete the square. That's going to be important in order to get it into vertex form. And then we also got to be able to transform our graphs. So vertical and horizontal shifts, reflections, stretches, compressions, all that stuff. So if we look at example 1 here, they give us a bunch of data. Just like we did yesterday, the most important thing is to plot that data. We'll give you a graph. Make sure your scales on the graph are good. In this case, we have the scales given to us. Now, if we look at this graph, here, yesterday we found the line of best fit, right? So we'd find a linear function or a linear equation that best represents that data. Well, if we notice, based on the data points that they give us, that line would not be a very good projection because we can see the data continues to go up in a quadratic manner, and our line of best fit would not represent that data. So by looking at those data points, we created the scatter plot of the data, and then now we're going to graph the regression line and the quadratic model. So actually, in this case, they're asking us for a linear regression. So that line of best fit that represents it in a linear relationship, and then the quadratic model. So then we're going to use the data point and find a quadratic best fit graph to represent these data points. Now, if you remember from yesterday, we showed you how to do it on the calculator. So I'm going to go ahead and just go through this. If you don't remember how to type them in on the calculator, go ahead and look back at day 1, enter those data points, go through that process, and then apply it here. But we get this equation right here. So this equation, y equals 23.83x minus 113.75. That's the linear regression that's best representing this data model. Now, moving on to the quadratic model, which we said just by looking at these data points is probably a better representation of our data. We're going to go through the same exact process for the most part. On your calculator, you're going to hit stat edit just like you did on the linear regression. And then actually, since you guys already did the linear regression on your calculator, your x and y values should already be in place on the L1, L2. And then all you have to do is, just like you did on the linear regression, go ahead and hit stat calculate. But now instead of doing a linear regression or a linreg, we're going to do a quadreg. So that's the quadratic regression. Hit calculate, and then it's going to spit out your A, B, and C values, just like we had on the linear regression. So when we see that, we're going to end up with A being 0.75, So it's 0.75x squared minus 2.42. That's our b value that came up on the calculator. And then plus 17.48. So this is our quadratic regression, our quadratic model of best fit for this data. Okay? So that's the linear regression representing that table and the quadratic regression. Now, if we look on part B, it says use each model to predict the number of miles for 1990 and 1998. So if 1990 was 1145.94 and 98 was 1585.74, find the percentage error for each model. Well, first, what we got to do is we got to predict the number of miles. So let's go ahead and do our linear prediction over here. So if we're looking for 1990 and 1998, we got to look at our data table. It's telling us that x equals 0 represents the year 1950. So if we're looking for the year 1990, then we just got to find f of 40, because this is 40 years after 1950. 1990 would be 40 years after 1950. So we plug in 40 for x, and then we would do the same, but we would plug in 48 for 1998. And when we plug those in for the linear model, you're going to get 839.45, and you're going to get 1025.29. Okay? So again, all you're doing is you're plugging in these two numbers into your equation, which we found up here, for x, because x represents the years since 1950, and these are the predictions. Okay? Now, if you remember, anytime we want to find a percentage error, we had that formula yesterday, so you can go ahead and look back at that. But if you recall, that formula would be the actual, or the absolute value of the actual, minus the estimate, or the prediction, close the absolute values, all divided by the actual. So if we apply that here, that should have some more space, but if we apply that here, for 1990, it says that we have 1145.94. So we have 1145.94 minus 839.45 all over 1145.94. And that percentage error, if you type it in, would be 26%, roughly. Okay. So in 1990, the prediction was 839.45 with a 26% error. So that means if that was your prediction, what actually happened in 1990 was had a percentage error of 26%. And then if we did the same thing for 1998, we can go through that. That prediction, or that actual, was 1585. 1585.74 minus 1025.29 all over 1585.74. And that result was 35%. So in 1998, the prediction, or for 1998, the prediction was 1025.29 with, should I predict? 1025.29 with a 35% error in their prediction. Okay, so that was the linear prediction and the percentage error for that prediction. But it's asking us to do it for both, so let's go ahead and use our quadratic model And if we do that, we're doing the same thing. You need to plug in 40, and you need to plug in 48, because again, X represents the number of years since 1950. So in 1990, that's been 40 years after. In 1998, that's 48. And again, we're plugging in for both X's, being very careful and precise in how we're plugging them in. And if we do that, or when we do that, we get 1120.68, and we get 1629.32. Okay. Now again, when we go through this to find the percentage error, we can already tell that in 1990, our prediction's a lot closer than it was for our linear model, right? If we had 839 was a prediction and it actually ended up being 1145, we were off by 26%. We can already tell, because our prediction's a lot closer to the actual result, that this should be a way lower percentage error. So if we go ahead and use this formula, actual minus estimate divided by the actual, we get the percentage error would be 2.204. And then we can just, again, go through the percentage error on this one would be 2.748%. So for the quadratic model in 1990, we predicted 1120.68 with a 2.204% error. And in 1998, we predicted 1629.32 with a 2.748% error. So again, this kind of just confirms that that data table was a lot better using a quadratic model than a linear model, because we can just tell from the numbers themselves, but even more so showing mathematically with the percent error calculation, that our quadratic model was way more accurate as to what actually happened. Now, for part C, why does the y-intercept mean? What does the y-intercept mean in the linear and quadratic models? What does the slope mean in the linear model? Well, let's start with the y-intercept in both models. The y-intercept means that your x value is 0, right? Obviously, that's what a y-intercept is. So if we look at our y-intercept here, it's telling us that when x was 0, meaning in 1950, because we know that x equals 0 is 1950 based on what it tells us in the table, there were negative 113.75 air passenger miles. So just saying that out loud makes no sense. So in the linear model in 1950, they had negative 113.75 billion air passenger miles. And this makes no sense. So we need to explain it, but obviously that's just kind of explaining exactly what the confusion is here and why that one didn't work as well. So for the quadratic model, we can kind of do the same thing. In 1950 they had, but this time 17.48 billion air passenger miles, right? And in this one, it makes a lot more sense. And they're starting at 1950. They had 17.48 billion air passenger miles. That's an actual number that you can begin with, and it represents our data pretty well. And it's pretty close to the actual table, right? So our equation, the quadratic equation that we have, again, is an estimate or a line or a quadratic model that represents the actual data that was happening, and it's pretty close to that 16.94 billion. Now for the slope in the linear model, the slope is telling you that each year, for every 1 year, they increase by 23.83 billion air miles. That's what a slope is. So for each 1 year, they increase by that amount. Okay. On to the next page. If we take a look at number 2, it says graph the quadratic function, specify the vertex, axis of symmetry, maximum or minimum value of the function, and the intercepts. So if we look at this one, you guys can do this, or you know how to do this using the negative b over 2a and then plug it back in for x to find your y value for your vertex. But one thing we're focusing on here for today, we're going to use that front side, and we want to get this to vertex form. So I want to work through that process here. One thing to get to vertex form, the first thing you got to do is move over that constant. So if we have y plus 1 equals x squared plus 6x, the reason we want to do this is I want to complete the square on the right side to make it a lot easier to get into vertex form. So by getting rid of that constant, now, again, if you remember, the way we complete the square is we take that b value, and we're going to be adding a new number to the right side, and we take that b value, 6, we divide it by 2, and then you square that result. Okay? Now remember, what you do to one side, you have to do to the other, so be very careful as you do this. Make sure you add it to both sides. Well, we all know 6 divided by 2, that's 3. We're squaring, so what we're doing here is we're adding 9 to both sides. Okay? So again, we're just adding 9 to both sides, so this is going to end up being y plus, that's 9 plus 1, so y plus 10. Ooh. Is 10. And then on the right side, we have x squared plus 6x plus 9. And then the reason that we completed this square is now we can factor that right side. And when we factor it, x plus 3 times x plus 3, it becomes two binomials that are the same. Now this is really nice because then we can move that 10 back over to the other side, and now we have the vertex form that we were looking for, which makes it a lot easier to graph. Okay, so again, move that constant over, complete the square on the right side, and then once you've done that, then you can move that that constant back with whatever you added to both sides. So now that we have it in vertex form, we can specify the vertex, which is a lot easier because we just have to look here. Remember, opposite inside, exact outside. So the vertex is -3, -10. So -3, -10. Go ahead and plot that. And then the axis of symmetry, since we know the vertex, we can just say that the axis of symmetry is x equals whatever that x value is. Now, looking for a maximum or minimum, we know from the vertex form that this a value is 1, which means it has to open upward, which means that that vertex, the y value of the vertex, is going to be a minimum, not a maximum. So the -10 is our minimum because it is opening upward. Okay. Now, we know that it opens upward, but we don't know how wide or narrow. So what we want to do here is find an X-intercepts or the Y-intercept. So it's specifying that we have to find the intercept. So let's go ahead and find the Y-intercept. Y-intercept's a little bit easier because, let's use a different color here, because if we look for the y-intercepts, you can use either form. You can use the standard form that it gave us at the beginning, or you can use the vertex form. Well, for a y-intercept, it might actually be easier to use the standard form because for the y-intercept, you know x equals 0. So if I plug in 0 for these two x values, I know that my y is going to be -1. So we know the y-intercept is at 0 for x, -1 for y. So our y-intercept as we just said, 0, -1. And there we go. So we can graph that. 0, -1. And then the nice thing is, because that we have that axis of symmetry, if I go straight across, that's 1, 2, 3 units this way. I can go 1, 2, 3 units right across that, because we know parabolas have a symmetrical shape. The final thing we need to figure out is the X-intercepts. And so for the X-intercepts, on the other side of it, it would actually be easier to use the vertex form, because we have to plug in 0 for y. So if we use the vertex form, 0 equals x plus 3 squared minus 10. Rather than foiling out that binomial completely, we can just move this 10 over. 10 equals x plus 3 quantity squared. And then since it's a binomial with quantity squared, it'd be really easy here to just square root both sides. Don't forget the plus or minus. These cancel out. We got to go laterally here. We have plus or minus root 10. Root 10 equals x plus 3, and then just subtract the 3 over. So we know x equals -3 plus or minus the square root of 10. And these are your two x-intercepts. So if we go ahead and write them here, your x-intercepts are 0, not 0 for x, 0 for y, -3 plus root 10, comma 0, and -3 minus root 10, comma 0. And there you go. We take the root 10 as an equivalent answer. You can also reduce that radical. So go ahead and pause the video here. We got another example for number 3. Go ahead and pause the video for a second. Try it out on your own, and then unpause it and check your answer. So as we look through number 3, we got it worked out here, but just as we did in the last one, remember you move the constant over, and then in this case it doesn't work out perfectly. You have to take the 3, divide it by 2, and then square it. Well, 3 divided by 2 quantity squared is 9 over 4, and then that 9 over 4 x squared minus 3x plus 9 over 4 factors to, again, because you completed the square, two binomials that are the exact same. Okay, and then you follow through the rest of the steps, graph them just like we did on the last one, and there you go. Notice it does not have an x-intercept because we start our vertexes above the x-axis and it opens upward. For number 4, it's asking us to determine the input that produces the largest or smallest output. Say whether the output is the largest or the smallest. What it's asking for here is it's asking for the vertex, right? If it's talking about the largest, that's going to be a maximum at the high point. If it's the smallest, that's going to be a minimum at the low point. So since we don't have a graph to work with, it's got a pretty narrow area here. One thing we got to do is we got to complete the square and get it in vertex form. That would make it a lot easier to determine if it's a maximum or a minimum. Now, very, very carefully, we got to make sure you cannot complete the square until your a value is 1. So the very first thing you got to do, actually before we even do that, to make it easier, is let's go ahead and move over the 11. Because, oops, that's not a 10. Move over the 11. Because remember, if we're going to be completing the square, we have to use these parts with the x variable. So now the most important part is go ahead and factor out that 2 so that we have y minus 11 equals 2, and then x squared minus 2x. Do not forget to factor out that a value that you did on that second term. Now on the inside, This is where you got to be careful. Go ahead and complete the square. So 2 divided by 2, we're going to add 2 over 2 squared. So one thing you got to be careful with here is we have y minus 11 equals 2 times x squared minus 2x. And then we added 2 over 2 is 1 squared. We added 1 to the inside here, right? Now remember, what you add to one side, you must also add to the other side of the equation. But we didn't add 1 to the right side because this is inside of these parentheses. So the value we actually added to the right side is 2, right? Because that 1 is being amplified by that GCF out in the front. So we actually have to add 2 to the other side. So you got to be careful with that. If you factored out an A value, when you complete the square on the inside, you got to make sure you account for it on the other side of that equation. So we have y minus 9 equals 2, and then that perfect square factor is x minus 1 quantity squared. And now we can go ahead and move it back. So we have y equals 2, x minus 1 quantity squared plus 9, and here's your vertex. Now to answer the question that it's asking is determine the input that produces the largest or smallest output. Well, we know input is your x value. So the input is 1. That will produce the largest or smallest. How do we know if it's the largest or smallest? Well, if we can just visualize this graph here, with the A value being a positive 2, it's got to open upward. So the input of 1 is going to give you the smallest output being 9, because y is your output. Okay. So again, be very careful when you have an A value that is not 1. Make sure you move that constant over and then factor out that A value before you complete the square, and make sure when you do complete the square, you take into account that A value on both sides. The last one here, number 5, if you're feeling really confident, you can pause it and then watch the rest of the video as I work through it. Otherwise, I'm just going to kind of go through this with you, and then you guys can go ahead and try that homework. It says find the value of A given that the maximum value of the function is, of that function is 5. So we're going to do something very similar, basically the same thing as it was on the last, but now we got variables involved. So the first thing we got to do is move that negative 4 over. So we have f of x. Now let's just call it y. Let's just call it y for now. We'll make it f of x back at the end equals a x squared plus 3x. Now again, before you complete that square, you got to factor out that a value. So we have y plus 4 equals a times x squared, but then since we factored out an a value, we need to divide this 3 by a. So that's plus 3 over a x. Now this is where it gets a little bit tricky, but just follow your rules for completing the square and you'll be all right. What we got to add to the inside here is 3 over a divided by 2, so we can put that 2 in the denominator, quantity squared. Now, what did we add to this right side? Well, on the inside, we added, let's use a different color here. On the inside, we added 9 over 4a, right? 4a squared even. Ooh, be careful. 9 over 4a squared. But we have this a out in front. So the number that we actually added was 9 over 4a squared times that a. Well, one of those cancels out. So what we have to add to the left side is 9 over 4a. Okay. Got to be very careful about that. Now, y plus, and then put this whole value, because they're not like terms, on the inside, equals a times, and then what is this inside factored as? Well, it's going to be x plus 3 over 2a quantity squared. Okay, if you write out that 9 over 4a on the inside, if I wrote this out right here, 9 over 4a squared, you can probably process through that a little bit more. Okay, so now what we got is we got that right side factored, ready to go, and now we have to just move this one back to the right side, and we'll make that y f of x again. So f of x equals a times x plus 3 over 2a quantity squared minus, again minus, opposite, 4 plus 9 over 4a. Now again, it looks really messy with these a values and all over the place. But we have it in vertex form. Now again, we didn't really answer the question yet. Remember, the question is find the value of a given that the maximum of the function is 5. So this is where we did all that math work as far as completing the square and getting it into vertex form. But now we need to think and understand what it's actually asking for us to do. Well, we know that the vertex, right? The vertex is this value, comma this value. So that's a coordinate. It's just in terms of a. But it's telling us that the maximum value, well, the maximum value is your y value of your vertex, right? Well, in vertex form, where is the y value of my vertex? Well, the y value of my vertex is right here. I didn't point it out before, but you got to be very careful about this negative here. But the y value of my vertex is right here. So now all we have to do is understand that since the y value of my vertex is 5, and that represents the y value of my vertex, I can just say negative 4 plus 9 over 4a equals 5. And then again, as always, be careful with those negatives. Negative 4 minus 9 over 4a equals 5. Negative 9 over 4a equals 9. And then 36a equals negative 9. A has to be negative 1/4. Okay. And then if we want to take it even one more step further, and we're at the very end here, we did answer the question. So if this was the question, you'd be done. But if we wanted to put it into or write the equation, we can find this equation now. We have the a value. We have negative 1/4 x squared plus 3x minus 4. And this is your function where the maximum would be 5. Okay. So go ahead and try out the homework and check your answers online.